Good day from Chem Help ASAP. This video describes a recent reaction in which I encountered a mystery concerning the reaction product. During the experiment, I relearned the valuable lesson on the danger of making assumptions about your data. I'll walk through the story. Maybe you can figure out the mystery more quickly than I did. Here is the reaction. I posted a video on this experiment. This reaction is nothing special. It's just an SN2 reaction between an amine, an aniline NH2 group, and a primary alkyl halide. It looks very unremarkable, so let's just skip ahead to what went wrong. Here are two TLC plates. The plate on the left is the reaction. On the far left is the halide starting material. The second lane is the aniline starting material. The two right lanes are different concentrations of the reaction. When I took this TLC, my interpretation was that the aniline was completely consumed or nearly completely consumed. There is a shadow in the reaction lanes that lines up with the aniline. So since one of the reagents is consumed, the reaction is done. I did file away in my head that the reaction likely still contains some of the aniline. Great, so the TLC on the right is the isolated reaction product. See that shadow? It's very faint under what is presumably the product spot. In my head, I said, aha, there is the small amount of residual aniline starting material. As I look at these plates side by side, I don't think those spots line up. I doubt they have the same RF. Being in a hurry, I did not measure my RF values for both plates to make a comparison. Truth be told, I did not make up fresh developing solvent for the second TLC plate, so the mobile phase probably did not have the same composition, and therefore nullifying the comparison of RF values anyway. Of course, in my mind, I didn't need to compare the TLC plates. The TLC plate looked just as I expected, and everything was proceeding normally. Let's now move to the NMR spectrum. Here is the NMR. The spectrum looks great, but it is far from perfect. Let's first point out the NMR solvents. We have DMSO and water. We can ignore those peaks. Now let's look at the little impurities. Two peaks stand out. There is one at about 5 ppm and another around 6.4 ppm. In my mind, I'm expecting an aniline, one of the starting materials, specifically para-toluidine as an impurity. These peaks kind of match parts of para-toluidine. The NH2 could be this peak around 5.0. The peak at about 6.4 ppm could be these two hydrogens on the aromatic ring. If you look closer, the match is not very good. Both the NH2 and these two hydrogens should have the same integration. They don't. I, however, was not looking closely. I just wanted to make sure the signals matched my expectations. It's not a very scientific way to look at data, but that's where I was coming from. Whether I identified the impurity correctly or not, I did recognize that the crude material does indeed contain an impurity. While I did not put it in the video on the reaction, I did do a recrystallization of the crude product from ethanol. Getting this material into solution was not trivial. That was the first thing that made me think something was amiss. The NMR of the recrystallized material looked essentially identical to this same spectrum. Same impurity peaks and nearly identical relative integrations. That was a sure sign that I did not understand the situation. The proposed impurity, para-toluidine, should be very soluble in ethanol and easily removed through a recrystallization. Let's go back to the TLC plate. Here are the plates again. After a second look, with the help of the NMR, I knew that the impurity spot in the isolated product was not para-toluidine, our aniline, but both the NMR and TLC agree that there is something else present. What is it? This is now the mystery. Here is the reaction again. The reaction involved almost exactly a 1:1 molar ratio of the halide and aniline. Of course, just because I use them in a 1:1 ratio does not mean they will necessarily react in a 1:1 ratio. This is an SN2 reaction. It's quite possible that the amine in the product could bump into another molecule of the halide and do another SN2 reaction. That would give this bottom product. I knew that this double SN2 product was a possibility, but very early in the experiment, I convinced myself that the impurity was the aniline starting material. Now that I've looked more closely at the data, the double alkylation product seems much more likely. Let's go back to the NMR data. Now we're back at the NMR data, a bit zoomed in, with our desired product. Let's call it P. And our likely impurity, let's call it I. If I'm correct on the two structures, then all the hydrogens for both of these molecules should be present in this NMR spectrum. It's important to keep in mind that while both molecules are present in the product mixture, both molecules are likely not present in equal molar ratios. Let's use these peaks, their multiplicities, chemical shifts, and especially integrations to see if we can confirm the presence of these two structures. One thing that makes the task more difficult is that the two compounds are very similar and share many peaks that overlap. For this reason, I want to start the analysis on two peaks that I think are likely distinct for each molecule. The first peak is here at about 5 ppm. I'm confident that this peak, a singlet, rises from the impurity. It comes from these four hydrogens, identical by symmetry in the molecule. If these four hydrogens show a relative integration of 0.33, then each hydrogen on the impurity has a relative integration intensity of about 0.08. That's 0.33 divided by 4. The next key signal is at about 5.6 ppm. I believe that this triplet arises from the NH in the product. So if this one hydrogen shows a relative integration of 1.00, then each hydrogen on the product has a relative integration intensity of about 1.00. These two numbers, 0.08 and 1.00, represent the relative molar ratio of the product and impurity in the mixture. Let's see how we can use these numbers to analyze the NMR data. Here is a big table. There is one row for each NMR signal. The first column is the chemical shift value of the signal, and the second column is the integration value. The remaining columns allow us to make predictions and see if the observed values match our expectations. I've highlighted two rows for the two peaks we have already discussed. At 5 ppm are the two CH2 groups on the impurity. The observed integration is 0.33. Each hydrogen from the product would contribute a value of 1 to the integration, but we don't think the product has any hydrogens in this signal. So the product contribution will be 1 times 0, nothing. Each hydrogen in the impurity would contribute a value of 0.08. That's a number we determined on the previous slide to the integration. And we think the impurity has 4 hydrogens here, 2 CH2 groups. That would give a total expected integration of 0.32, 0.08 times 4. That is a good match to our observed value. At 5.6 ppm is the NH on the product. Product hydrogens have a relative intensity of 1, and there is 1 hydrogen giving rise to that signal. The impurity does not have any hydrogens in the signal, so the impurity contributes nothing. Our expected integration would be 1.00. It's 1 times 1. That's a perfect match to our observed value. Okay, that's the general idea. Let's now work through these other signals, the other rows, and see if the experimental values match the observed values. We might not get a perfect match, but it should be very close. First row, a signal at 4.6 ppm. It has an integration of 1.96. I believe that this is from the CH2 on the product and nothing else. That would give us an intensity of 1 times 2H. Nothing from the impurity, 0.08 times 0H. The expected integration would be 2.0. Well, that's a very close to our observed value of 1.96. Great. The next row is 6.4 ppm with an integration of 0.18. Based on this small integration, this peak must be from the impurity. Let's go back to the spectrum slide. This peak is at 6.4 ppm. It's tiny. It's from the impurity alone. I believe this to be the aromatic hydrogens on the aniline ring closest to the nitrogen. Both hydrogens on either side of the nitrogen. Okay, so the contribution from the product would be 1 times 0 hydrogens. The impurity would be 0.08 times 2H, 2 hydrogens. The expected integration should be 0.16. It's pretty close to the observed value, 0.18. Looking good. Next is the doublet at 6.6 ppm. I think these are the aromatic ring hydrogens next to the nitrogen on the product. We would expect the product to contribute an intensity of 1 for each of these 2 hydrogens. The impurity will contribute nothing, an intensity of 0.08 for 0 hydrogens. That gives a total expected intensity of 2.00. Great. Another very close match. These are easy so far. The next row is 6.8 ppm. This is a little more complicated. I think this signal arises from the other aniline ring signals for both the impurity and the product. So for the product, we should have an intensity of 1 for 2 hydrogens. For the impurity, we should have an intensity of 0.08 for 2 hydrogens. That's a total expected integration of 2.16. Very close to the observed value of 2.11. I suspect you're getting the hang of this, so let's deal with the rest of the downfield peaks in one group. Here we are back on the spectrum. These remaining downfield signals from about 7.5 ppm and higher are all from the aromatic ring attached to the carbonyl. Note that the product has one of these rings, while the impurity has 2. Our math will still work just fine. In total, the product should contribute 5 hydrogens to these downfield peaks. The impurity will bring 10 hydrogens because it has 2 rings. Back in our table, here is our chemical shift range and the total integration for all these peaks. The product brings an intensity of 1 for its 5 hydrogens. The impurity brings an intensity of 0.08 for its 10 hydrogens. the total expected integration should be 5.8, very close to the observed total of 5.73. Fantastic. Let's now get the methyl group, the CH3 singlet, at 2.2 ppm. This is the methyl group off of the aniline ring. The product has an intensity of 1 for its 3 hydrogens. The impurity has an intensity of 0.08 for its 3 hydrogens. The total expected integration is 3.24. Not as good a match as the other peaks, but not bad. Collectively, the NMR data strongly support that the impurity is in fact this molecule in the bottom left of the screen. We could gather other data, but I'm comfortable with this structural assignment, which seems very consistent with both the reaction and the characterization data. I think this mystery is solved. Looking back, how could I have prevented my confusion that I encountered in this reaction? First, I could have performed both TLCs under carefully matched conditions. No using a mobile phase that was prepared well over an hour ago. If the TLCs were better matched, I could have quickly checked the RF values and avoided the idea that the impurity was para-toluidine. Second, I should have been less convinced with my expectation that para-toluidine was the impurity. This expectation caused me to only look for what I wanted to see in the NMR spectra. Another mistake, scientists examine data before generating conclusions. I looked at a subset of the data, made my decision, and then disregarded any data that did not fit my expectations. Granted, I figured it out eventually, but I could have saved myself some headaches if I had done things right for the first time. That's the end of this mystery. Make sure you always test your conclusions against the available data, not the other way around. Please subscribe, like, or leave a comment. Take care.